Okay, so permutations part B, what we're going to look at here is just two specific examples of some unique permutations that I didn't feel like including in the last lecture that we did. So the first different kind of permutation would be, what if you had a group of objects that you wanted to rearrange, but some of those objects were things that were repeated. So say like multiple number fives. Okay, so when you rearrange these objects, you can't distinguish one 5 from the other 5. And so what you have to do, you're going to get less permutations than you normally would, because say those 3 5s that you have there, each time you choose one of those 5s to put into your arrangement, we don't know which 5 it is. So they're all kind of alike. So what we're going to do is we're going to take the total number of objects that we're trying to rearrange, and then we're going to do the factorial of that, and then you divide by each of the objects that are being repeated, factorial. So, say you had those 5s that were repeated, you had 3 of them, so you'd have a 3 factorial that you would have to divide by. And so you had another number that was repeated. Say the 2s were repeated, and you had 8 2s, so you'd have 8 factorial down here. Now I have R, S, and T, but that doesn't mean that you have to use all of those. Maybe there's only one number that's being repeated, and so you'd only have that one factorial in the denominator. Okay? So I call this the permutation, I call this the banana formula, because I like to use the word bananas to use as an example. So how many permutations will you get if you rearrange the letters of the word bananas? So first of all, we look and we see 1, 2, 3, 4, 5, 6, 7. There are 7 letters in this word. So the 7 factorial is going to go on the top. And then we look and see there are 3 A's, which you can't distinguish one A from the other A. So we have 3 factorial that's going to go on the bottom to represent the 3 A's. And then we also have 2 N's. So N is repeated. So that's the 2 factorial down here. Now, there is no fancy button, like the NPR button, but you can use your factorial button, and you can simplify if you want, and you should get 420 different permutations. Okay, so that's the banana formula. When you have multiple objects that are alike within your permutations. All right, the next one is a circular permutation. So what if you needed to rearrange people, say, sitting around a table, a round table, or anything that's circular. And you want to look at how many different ways can you do that. So what I have here with these green tables, it looks like these are all different permutations, but when you look at it more closely, you can see that each person is sitting next to the exact same person in each one of these permutations. So if you look at person Y is in between Z and X, and in fact X is to the right of him and Z is to the left of him. So now we look at person Y over here, and he may have shifted seats, but Z is still to the left and X is still to the right. Same thing over here. Z is still to the left and X is still to the right. Okay, so what has happened up here is that everybody has stayed in the same relative position with respect to each other, but they've just all like stood up and moved seats, just moved around the table one seat, and then sat down again. So that's not the type of circular permutation that we are concerned with. What we want is everybody to be sitting next to a different person. So these all are different seating arrangements, so they're all sitting next to different people each time. So the way you're going to figure that out is by actually taking one of the people and making them stay where they're sitting, and then everybody else gets up and starts moving around for each time. So for example, over here we have X in this position, and then Y, Z, and W. And so in the next, we'll go down here, in this permutation, what happened was Z stayed where it was, and that's fine, but Y and W switched places. Okay? Over here, Y stayed where they were, and the Z and the W switch places. So it looks like Y, Z, and W, they all start rearranging themselves, but X stays where they are. Okay, and this is how you get the true number of circular permutations. So what's happening here is, out of the 4 people that we were rearranging around this table, one of them is fixed, and then the other 3, you want to look at how many permutations you would get. So our formula, naturally, should come out to be n minus 1 factorial, because you're looking at that 1 less of the number of objects that are going around the table, factorial, to get their permutations. So if we look at our previous slide where there were 4 people sitting around a table and we use this formula, we had 4 minus 1 factorial, which is 3 factorial, which does in fact come out to be 6. And we saw there at the bottom there were 6 different tables. Okay, so let's try one last example. In how many ways can King Arthur arrange 8 of his knights around the round table? Well, we have 8 knights, but one of them is going to stay fixed. So 8 minus 1 factorial, which is 7 factorial, and punching that into the calculator, we get 5,040. Okay, so there you have it, those 2 specific types of permutations. We've got the banana formula, and we've got the circular permutations. Okay, that's it.